In this lecture, we'll talk about barometers and manometers. These devices are used to measure pressure, barometers specifically for atmospheric pressure and manometers to measure pressure differences between something in the atmosphere. And they both rely on using the hydrostatic pressure distribution, which was covered in a previous lecture. So let's go ahead and get into the material. Take a look at your screen. You'll see a picture of a very large typhoon called Typhoon Tip. This is the largest known tropical cyclone that's ever been recorded in history. You can see it's huge. It reached from New York to Dallas. It actually didn't happen here in the U.S. This cyclone actually, or this typhoon actually happened in the Philippines back in 1979. And it's just shown here, superimposed over the U.S. to show how massive it was. And the reason I'm showing the picture here is because Typhoon Tip corresponded to the lowest atmospheric pressure ever recorded. And we use barometers to measure atmospheric pressure, so I thought it was kind of a neat and interesting example to use for that. So we'll talk a little bit more about that later in the lecture. So let's go ahead and get into the material. First thing we're going to do is talk about barometers. So again, barometers and manometers are on tap for today's lecture, both of which use the hydrostatic pressure distribution, and they're both used to measure pressure. Okay? So a barometer is used to measure atmospheric pressure. And the way a barometer works is you have a working fluid, which is shown in here in gray, that's enclosed within a partially closed tube. You can see the tube is closed on the one end and open on the other end. And the tube is filled with the working fluid. Mercury is the most common working fluid, and you'll see why in just a little bit. But it's completely filled with mercury, no air in there, and then it's turned upside down into this large body of mercury here. And then what will happen is, because of the weight of the mercury, it'll settle down in this tube, so there'll be a little bit of a gap up at the top there. That gap is not air, it's not a vacuum. What it is actually mercury vapor. What happens is the pressure right at the top surface of the liquid mercury is very low, and when you reach a low enough pressure, namely the vapor pressure of the liquid, it'll turn into vapor. So you know that from thermodynamics. If you drop the pressure of a liquid low enough, it'll turn to vapor. So this is actually filled with mercury vapor, and it's at the vapor pressure of the mercury. And the way a barometer works is we can measure this height of the column of mercury in the tube, and it'll be related to the atmospheric pressure. So let's just show how that works. What we'll do is we'll first start with a point here on the surface of the mercury. So that's the free surface. So that pressure there is atmospheric pressure. And we can move horizontally, as you know from the hydrostatic pressure distribution video, that if you move horizontally in the same fluid, it'll be the same pressure. So that's also atmospheric pressure. So both of those are atmospheric pressure. And so what I want to do is find the pressure right at the top. The pressure at the top, of course, is going to be vapor pressure. And so what I'll do is I'll start at this pressure, P atmosphere, and then subtract out the weight of the working fluid as I move from this point up to that point. So this is the pressure I'm starting with right there, P atmosphere, and then I'm moving upward to this point. And as I move upward, I subtract out the hydrostatic pressure contribution of the working fluid. So I'm subtracting out the density of the fluid times gravity times the height that I've moved. So the pressure is now lower. And of course, the pressure right there is the vapor pressure, which is right given on the left-hand side. So this is the way that we work our way through barometers. And you'll see the same thing with manometers. As you start at a point where you know, and then you move up and down and add in or remove and add in the weight of the fluid until you get to the point that you're interested in. Okay, so you'll see us do this again in a couple of more examples. All right, so now we have an expression for the vapor pressure in terms of atmospheric pressure. Let's rearrange that. So we solve for atmospheric pressure instead of vapor pressure. So we have that expression. We'll do one more little thing here. So first of all, we could use the equation as it is. If we know the vapor pressure of the mercury, the density of the mercury, and we read the height of the column, then we can calculate what the atmospheric pressure is. The vapor pressure, however, is a really small value. I think the vapor pressure for mercury is on the order of 0.1 pascals, whereas atmospheric pressure is about 101 kilopascals. So the atmospheric pressure is much, much larger than vapor pressure. So it's reasonable to neglect the vapor pressure here. So we'll just say that the vapor pressure is much, much smaller than P atmosphere. So that P atmosphere is roughly equal to density of the working fluid times G times H. So by measuring the height of the column of fluid and knowing the density of that fluid, we can calculate what atmospheric pressure is. So that's how a barometer works. And I show a picture of a barometer over here on the right-hand side. Let me zoom in on it a bit. So here you can see this is a barometer. There's mercury is the working fluid. There's the kind of the large vessel containing the mercury, and it goes all the way up to seems to be about right there, that point right in there. It's a little tough to tell. So that's what a real barometer looks like. There's a thermometer in here to measure the temperature. The temperature will affect what the density of the mercury is as well as the vapor pressure. So it'll have some small effect on the measurement that you read. So the thermometer there is for improved accuracy. I'm not sure what this thing is over here. I couldn't read what it was, so I'm not quite sure what that is for. So let me now talk a little bit about why mercury is most commonly used in barometers. So we know that the atmospheric pressure at standard temperature and pressure is 101.3 kilopascals absolute, right? So let's just work our way backwards to find out what the height of a column of mercury would be corresponding to that pressure. We know the density of mercury is about 13,600 kilograms per cubic meter. And if we work our way backwards, then H comes out to be 0.76 meters or 760 millimeters or 29.92 inches. So a barometer using mercury will have roughly a height of about 3/4 of a meter, roughly 30 inches. So it's very reasonable height. You can put it on a desktop. It's easy to put in the laboratory. It's a convenient height to work with. Let's go ahead and see what we get when we deal with water. So if you use water, which is 1,000 kilograms per cubic meter, the corresponding height comes out to be 10.3 meters. Well, 10.3 meters is a pretty big distance. That's the height of roughly, a 3-story plus building, right? It's very tall. It's something like 34 feet, something like that. Making a barometer with water as your working fluid is very inconvenient. It's not going to fit in the laboratory. It's going to fit on the side of a tall building, right? So you're just not going to use water. It's just too inconvenient. Even though mercury is toxic to handle, you have to be careful with it. It's just so convenient that it's just the default fluid for barometers. A couple of other things related to this. First of all, you'll see that 1 atmosphere, 101.3 kilopascals, corresponds to 760 millimeters of mercury or 29.92 inches of mercury. So sometimes you'll see people report pressure in terms of millimeters of mercury or inches of mercury. It's just another unit that's often used for reporting pressure. So I'll just write this over here. So one atmosphere, which is 101.3 kilopascals, is also 760 millimeters of mercury or 29.92 inches of mercury. It's just another set of units that you'll sometimes see people report pressure in, just because of the idea that you can use mercury as a working fluid to measure the pressure. It's probably most commonly used in the meteorological area. Okay. Since barometers are primarily used for measuring atmospheric pressure, let me give you a feel for some numbers when we talk about atmospheric pressure. So, of course, 1 atmosphere, a standard atmosphere, corresponds to, I'll do this in inches of mercury, this corresponds to 29.92 inches of mercury. The reason we measure the atmospheric pressure, the reason that's of interest meteorologically, is because when the pressure drops, that typically corresponds to stormy, kind of bad weather. So when the atmospheric pressure drops, You tend to have bad weather. When the atmospheric pressure rises, you tend to have clear, dry weather. So that's why people monitor atmospheric pressure. When the atmospheric pressure changes rapidly, you tend to get very windy conditions, because what's happening there is when the pressure changes, you're getting a pressure difference, and that pressure difference pushes the atmospheric air, which is what we know as wind, right? So monitoring the atmospheric pressure can give you an idea of what the weather is going to be like. So just to kind of give you a feel for some numbers here, we said that standard temperature and pressure corresponds to 100, I'm sorry, let me do this in inches of mercury. This corresponds to 29.92 inches of mercury. A typical Midwestern thunderstorm, like what we might have in Indiana, will only drop the pressure a little bit. So it comes out just kind of roughly, shouldn't put equals, it's just roughly on the order of 29.8 inches of mercury. So, a small drop in atmospheric pressure can correspond to stormy conditions. Now, the Typhoon Tip that I showed at the very beginning of the lecture, so back up here, Typhoon Tip, this terrible, this huge storm hit the Philippines in 1979, caused a lot of damage, some deaths. This had the lowest atmospheric pressure on record. Okay, so that atmospheric pressure was 25.69 inches of mercury. So much, much lower, more than 4 inches lower than standard atmospheric pressure. So a real big drop in atmospheric pressure for this typhoon. A typhoon, by the way, it's just another name for a hurricane. Now, the highest atmospheric pressure occurred in Siberia. Just to kind of show you the opposite side of it. It occurred in Siberia back in, I think it was 1969. And that atmospheric pressure was 32.01 inches of mercury. So that's the highest atmospheric pressure that's been recorded. Back in the day when this high atmospheric pressure occurred, it was a very cold, clear, dry day in Siberia. The temperature was something like minus 50 degrees Fahrenheit. It's very cold. So that gives you a range for what typical atmospheric pressures would be, anywhere from 29.7 inches of mercury all the way up to about 32 inches of mercury, with just about 30 inches of mercury being, typical. Okay. Let me say one more thing before we move on to manometers, and this last thing refers back to this measurement in the barometer of, if we used water as the working fluid and we had atmospheric pressure, the column of water would be 10.3 meters tall. So let's imagine the scenario. Let's say we have a tall building and it's multiple stories. So here's 3 stories, 4, 5, let's say 6 stories tall. Now 10.3 meters gets us to about 3 stories, maybe a little more than that. Right? So let's say we wanted to get some water to the top of this building. Well, one way you could try to do that is to draw a vacuum. Let's say we had a pipe here that was this tall. What we could do is we'd have atmospheric pressure out here, and we could try to draw a vacuum right at the top of this pipe. And if we draw a vacuum at the top of the pipe, the highest the water will go in this pipe will be to the 10.3 meters. And the reason for that is because we just showed moments ago that if you had water in this barometer, the atmospheric pressure would just support the weight of a 10.3 meter column of water. It's the highest you're going to go. If you pull a vacuum up at the top, it's only going to go up 10.3 meters. So how would we then get water up to a 6-story building? So how's that possible? Well, the way we do it is we use a pump. And we use the pump at the bottom of the building. So what we'd do is we'd put a pump down here, and then we would pump the water in at atmospheric pressure, but the pressure right downstream of the pump, like right here, so it'd be atmospheric pressure going in, but the pressure there after the pump would be much larger than atmospheric pressure. That's the purpose of a pump, is to increase the pressure in the fluid. And by increasing the pressure, we can then push the fluid up a much higher distance. We could go to the top of the tallest skyscraper with no problem. if you have a well, for example, and you live out in the country and you get your water from a well, the pump that's used to pump that water is rarely put on the surface of the well. It'd only be put on the surface if the well is very shallow, less than 10.3 meters. Normally, for deeper wells, you'd sink the pump all the way to the bottom of the well so that you can push the fluid up more than 10.3 meters. Okay, so this is a topic we'll come back to later in the course when we talk about pipe flows that incorporate pumps. Okay, so that was the last thing I want to say about barometers. Let me move on now to manometers. Now, barometers used to measure the pressure of the atmosphere. A manometer is used to measure the pressure relative to the atmosphere, typically. So I show a picture of a manometer here. This is a manometer that's called a U-tube manometer. U-tube because it's in the shape of a U here. What we have is an open end that's open to the atmosphere, and then the other end is where we want to measure the pressure. So let's just say point A is what I want to measure the pressure of. What's the pressure at point A? And that's in, I have two different fluids in here. Fluid 1 is actually my working fluid, and fluid 2 is just the fluid within which I want to measure the pressure. Okay, and I have a couple of different height measurements in here as well. So let me just show you how we work our way through manometers. So what I want to do is I want to find the pressure at A. So I want to find the pressure there, but I'm going to start with the pressure at C, which we know is atmospheric. So pressure at C is right there, but that's open to the atmosphere. So that's atmospheric pressure there. Then I'm going to go from C down to this point. Let me call that point D. So the pressure at D will be the atmospheric pressure plus I'm adding in weight of the fluid. Because I'm moving down in the fluid, I'm adding some weight. The pressure has to increase to support the weight that's above it. And since I'm moving in fluid 1, then I'm adding in the density of 1 times G times the distance I've moved, which is HBC. Okay, so this is now the pressure at D. It's the pressure I started with, P atmosphere, plus rho 1 GHBC. Rho 1 because I'm moving in fluid 1, HBC because I moved a distance of HBC, and I'm adding in because I'm moving down, and so the pressure has to increase to support the extra weight. Now I can go straight across to point B. And the reason I can do that is because we know the pressure doesn't vary laterally as long as I'm moving in the same fluid. That's important. It can only be moving in the same fluid. If I move in the same fluid laterally, the pressure remains the same. So the pressure at D and the pressure at B are identical. Okay. Now I'm going to move up a distance of HAB to get to this point right here. Let's call that point E. So to get to point E, I'm going to subtract out some weight of fluid 2, and I'm moving a distance of HAB. So what's happening here is I'm now moving in fluid 2, so that's why I have a density of 2. I'm subtracting some weight out because I'm moving upward. The pressure is dropping because I'm removing some of the fluid weight by moving upward. So that's why I have a minus, and then HAB because that's how far I've moved. So this now is the pressure at E. But the pressure at A and the pressure at E are identical. And the reason for that is because now I'm moving just horizontally between A and E. So the pressure at E and the pressure at A are exactly the same. So the pressure at A now is just this that I've boxed in. So that's how you figure out pressures in manometers, is you look at where you want to find the pressure and then find the other end and then just work your way around adding and subtracting in the weight of the fluid. Just being careful of some bookkeeping, the proper heights, whether you're adding or subtracting, and taking into account the correct densities. Now one other thing that I'll show here is, let me rearrange this so that I bring the P atmosphere to the left-hand side. So if you look at this expression, it's the same expression, but the left-hand side I've written explicitly so that it looks like a gauge pressure. So you can see that what this manometer is doing is measuring the pressure at A relative to atmospheric pressure. So it's really measuring the gauge pressure at A. This is why we have the concept of gauge pressures, is because devices like manometers are measuring pressures relative to the atmosphere. It's very common. So that's why we use gauge pressures. Let me just talk a little bit about the picture on the right-hand side here. This came from an experiment where they were measuring pressure inside a balloon. We have this red balloon, and you can see there's a pump here that filled up the balloon to a pressure higher than atmospheric pressure, and it's connected to a U-tube manometer. There's a line here that the air in the balloon connects up to, and then we hit our blue working fluid here. It's probably just water with food coloring in it, and then the rest of the tube is just eventually open to the atmosphere up here. And you can see the pressure in the balloon is higher than atmospheric pressure because it's pushing down on this side more than over here. So the pressure here is larger pushing down than the pressure here, which is atmospheric pressure. So the pressure in the balloon is larger than atmospheric pressure. And if you measured the height here, you could figure out exactly what the pressure inside the balloon is, right? Because it's just a manometer and we can figure it out. Since you're dealing with air in this part of the manometer, you don't have to worry about the elevation differences of air. Remember from a previous lecture, we said that if we were dealing with gases and elevation changes of less than a few hundred meters, then you don't have to worry about how the pressure changes over that distance. It's insignificant. Okay. So that is a U-tube manometer. Let me show you an example of another manometer that's shown here. This is called an inclined tube manometer. Inclined tube because one of the arms here is inclined at some angle theta. This manometer operates the exact same way as the U-tube manometer. We analyze it very much the same way. The reason you have the inclined arm is because it's a more sensitive type of manometer. If you have some small distance here, some small elevation difference here at HBC, the more inclined the manometer arm is, the larger the distance L will be here. So small pressure changes get magnified because of that inclined arm. So let's analyze this one. So again, we'll say that we want to find the pressure at A, starting with the pressure at C. Right over here, well, the pressure at C is atmospheric pressure. Then we'll move to this point. Well, we've moved a distance HBC downward. Remember, it's only the vertical distance, the direction of gravity that we care about, right? Since gravity is pointing in the vertical direction, we only care about vertical distances. So we're moving down, so we're adding in the weight of fluid 1. We move down a distance of HBC. Well, that's the same pressure at B because we can move horizontally in the same fluid and it'll be the same pressure. And then if we move upward to this point, we'll be subtracting out the density of fluid 2 times G times HAB. And then that point is the same elevation as point A, so we now have our pressure at A again. It looks exactly the same as the other U-tube manometer analysis. It's just now that we have an inclined tube. Now normally we measure the distance along the incline, the direction or the distance L as shown in the picture here. So let's rewrite HBC in terms of L. So if I just do a little trigonometry here, the sine of theta is HBC all over L, so HBC is L sine theta. So then PA minus P atmosphere is rho 1 G L sine theta minus rho 2 G HAB. So you can see in this inclined tube manometer, we just measure the distance L to get our pressure measurement. Rather than the vertical distance, we just measure the distance at the incline, use a little trigonometry to get the actual vertical displacement. In a picture of a real inclined tube manometer shown on the right-hand side here, and of course it has this red kind of working fluid in here. This appears to be water since it says millimeters of water. But you can see the distance along the length here is what you measure. So it's kind of corresponding to the L distance here. So that's all there is to manometers. They come in different shapes and sizes, different kinds of working fluids. They're very cheap devices. They're used all the time. You don't have to do any calibration to them. And they don't cost much. You can make your own manometer. Just go to the hardware store and get some plastic tubing, fill it with water, maybe add a little food coloring. Boom, there you go. You have your own manometer. You can use it to measure pressure differences. Nowadays, manometers are still pretty widely used because they're cheap. But it's very common now to see electronic pressure transducers. So they use a piezoelectric kind of approach to measuring pressure, where if you compress on a crystal, it'll give off a little electrical current. And so those piezoelectric pressure transducers are used very commonly because they're very small and they have very fast response time. So if you can measure rapid pressure fluctuations with those kind of devices. Manometers have some inertia to them. You can imagine if you had a rapidly fluctuating pressure, the inertia of the water would be so much that it couldn't move fast enough to really capture those fluctuations. So manometers are usually best used for steady or almost steady kinds of situations. Anything where the pressure is varying rapidly, you'd want to use an electronic pressure transducer. All right, I think that's all I want to say about barometers and manometers.